Hello. My name's John Hawthorn. I'm a Ruby committer, a member of the Rails core team, and a staff engineer at GitHub. Today, I'd like to introduce you to Vernier. Vernier is a new open source Ruby profiler for Ruby 3.2+. It's a tool to help show you where your program's spending time, but also to better understand it. I'm going to start with a quick demo. Vernier comes with a CLI to easily measure a command. We're going to measure bundle update with a mostly empty gem file. So we can run that, wait for it to finish, and it will tell us it recorded a profile and where that file is stored. Next, we need to take that to a viewer program to see it. We have this is a single page web app. It's hosted at vernier.prof. And this is based on the Firefox profiler. It's just a light reskin. In fact, the main change we've made is we've swapped out the word JavaScript for Ruby. And that might sound a bit strange, but the Firefox team wrote their profiler with the intention that other tools would target it. But also, these projects aren't quite as different as you might think. They're both C or C++ programs which host a dynamic language, have a JIT compiler, and are multi-threaded. So looking at the things that the Firefox profiler provides and trying to find Ruby equivalents has been a good guide for building a good profiler. Once we drag the file into this viewer, this is what we'll be presented with. At the top, we'll see a timeline that shows a chronological representation of what your program's doing at every point throughout execution. As you mouse over, it will show you the stack so you can see exactly where the program was, as if an exception had been raised or you'd done puts caller or something of that sort. The lower part of the graph shows the same information, but with a flame graph or stack chart style visualization where things are layered on top of each other. And you can browse in here and really get a good idea of what your program's doing throughout execution. But this can be a bit busy and intimidating, especially on I guess it's a big screen, but on a slide. So I'm going to move over to the call tree view, which is more of a summary. This shows a top style list of which methods took the most time. And the first thing it shows us is not all that helpful, which is that main took 100% of our time. And we probably didn't need a profiler to figure that out. But we can switch this to a top-down view or bottom-up rather than top-down view. And now it will show us some more interesting things. So we see that it's spending time requiring, that it's doing some network stuff. That makes sense for bundler. But the top method we're seeing here might be a little surprising, string.split. I don't think this is that string.split is slow. It's probably just doing what we've asked, but we're calling it a lot or with a very large string. So we can expand that to see who's calling it. And there's two methods inside this bundler compact index client cache class. We don't have to know what those are. We can double click on that and it will bring up the source code. This is a feature on the vernier.prof site. We run a proxy that will fetch this from any public gem. Or you can use the profile viewer gem and it will fetch the source code from your local machine. In the left-hand margin, there's annotations showing the number of samples which have been collected for each line, which you can just think of as a relative measure of performance. And here we can get to the first unique feature of Vernier, which is that we can switch our data source from timings to allocations. So in addition to recording the time something took, we've also recorded the number of allocations it's made. And we put these both inside the same profile file because I really want these to be a single artifact that represents as much as we can about a program's run. So here we see that string.split, in addition to being the slowest thing, also made almost 1 million allocations. So very allocation heavy. So next, if we wanted to improve this, maybe we'd do something like take those lines, which are splitting a string, but then only it's splitting a string into 3 strings, but then only taking the first and last. We don't actually need that middle string or the array. So if we do this with a substring index, that might be faster. So let's see the result. Originally, this took about 0.6 seconds. And then with the small modification, it takes about 0.5 seconds, so 100 milliseconds faster. This is why I find performance work so fun to work on. We've made an improvement to Bundler without starting with any deep knowledge of how it works. We've, in fact, only gained knowledge about what things are important to Bundler. Clearly, this compact index and these strings we're splitting are a big part of how it runs. I just want to point out one thing I didn't do. We didn't use the profiler to measure the improvement. Profilers can introduce overhead and otherwise confuse the result, so it's really important to always measure without profiling enabled. So this is where what using Vernier is like today, but this wasn't the original idea I had for this profiler. Originally, back in 2022, when I started working on this, I had a very different problem I was trying to solve. I was trying to discover where a Ruby program's memory was being used. And there's some good built-in tools for this. You can use objectspace.traceAllocationStart, which will tell Ruby to start tracing where allocations happen. Then you can load your program and run objectspace dump all. This will create you a heap dump, which is a giant file that has one line for every object in your Ruby heap. So for GitHub's largest application, that's 6 million lines. It's about a 2 gig file, so it's massive. And each of those lines looks something like this when you have tracing enabled. It tells you about the object, and it tells you the file and line it was allocated from. And for many things, this can be quite useful. But there's also a lot of cases, like for message pack, where you just don't know. Like message pack is doing the best thing it can for you. It's loading whatever you told it to. And so I wanted to get more information out of this, ideally a full stack trace. The problem is that a stack trace would be very expensive to represent in this file. It's already 2 gigs, so I can't just store it uncompressed. So to improve that, the first thing I wrote for Vernier was a data structure to efficiently represent stacks, which is called the stack table class. So we can instantiate one of those, ask it to record the current stack, and then every time we do that, it will return us a unique integer that represents the stack we saw. And if you call it repeatedly with the same stack, you always get back the same integer. And then at a later time, you can reconstruct that back into a full backtrace. So this is a thing I'm sharing in part because I think this is a pretty interesting ability to have. I could see using this for things other than profilers. So if you have ideas, please try them out. The very important thing about this for the tracing, the retained memory profiler, is that calling current stack never allocates a Ruby object. Most of the time, it won't allocate at all if it's seen the stack before. But if it's a new stack, it will do an allocation in C, but not an allocation in Ruby. And that's because we want to measure the Ruby program. So we can't interfere with it too much by making allocations that might mess up the very thing we're trying to measure. So the representation of these stacks is a tree structure where each stack points to the subset of the stack that's the parent. And so we're actually even able to reuse parts that are common and shared between stacks, which is really, really common in a profile. And then we also deduplicate the frames which occur multiple times. So we end up with a very, very efficient representation, and conveniently this very closely matched the Firefox output format. So this is what it likes when you make a memory profile. Unlike the time profile here, the x-axis shows the number of bytes used. And for things like message pack, this can get us a much greater idea. So we're not just seeing that message pack read was where our memory was used. We can actually figure out that, oh, that came from loading IETN information. So I think this is a good tool. And after building this, I discovered that this was the great start for a more traditional more traditional time profiler. And there's a couple techniques there's two main techniques that can be used for time-based profiling. The first is a tracing profiler. In Ruby, you'd do this with the TracePoint API, where you can configure a callback that's called every time a method's entered, and another callback every time a method leaves. And you can just take the differences between those two times. This is how profile.rb, the original Ruby profiler, works, and that shipped with Ruby until a recent version, I believe. The problem is it can be quite slow. It introduces a lot of overhead. So if we have a Fibonacci program, for example, that takes 0.1 seconds to begin, if we run that with profile.rb, it's 500 times slower, which makes sense if you think that we're running an extra line of Ruby code for every line of Ruby code we run. But even if we implement this technique in C, it still ends up a lot slower. And there's two big problems with this. The first is that you're going to have a hard time running something this slow in production. You'll hit a timeout or impact users. But the bigger problem is that this doesn't slow things down consistently. A real Ruby program is a mix of things. Some of its time is spent running Ruby code, but some still is spent in native code, like usually a C function, like string.split we saw earlier. And most programs spend a lot of time idle, waiting on I/O, talking to the database, doing something over the network. And when we use a tracing profiler like that, all of the impact happens to the Ruby code. So we actually end up measuring a program like this, which doesn't reflect reality, where the time in Ruby has been inflated, but the other time stays the same. So in general, I think tracing is not the right solution, but it has some benefits. It's the only way to get the full information out of something. It's the only way to get the number of times something happened. And so Vernier uses a combination of both tracing and sampling, but in a very, very minimal way for tracing. The first way we use tracing is for user timings through something like Rails active support notifications, which will tell us about every database query that's made. And we can put custom things in here, and we can record extra information. So this is nice to have inside a profiler. But we also subscribe to some events that Ruby provides. For example, garbage collection. Vernier will subscribe to the internal garbage collection C API and record every GC pause that happens in your program. And this provides a really nice way to better understand the garbage collector, because it's easy to think about the garbage collector as something that's always running and taking up a percentage of time or taking a huge chunk of time. Whereas in reality, it's a sophisticated tool, garbage collector that has incremental marking. And this lets us better see that. So let's move on to sampling profiling. And this is what most modern Ruby profilers will use. The key of this technique is that we want to run something every so often. So we'll have an interval, which you could call a sampling rate. Here I've picked 1 millisecond, which is very typical. And then, so what we want to do every 1 millisecond is collect a sample. And here that's the backtrace from the main thread. So we can collect those, store them in an array, and then as our program runs, we'll end up with this big array that shows us where our program spent its time. And this is, I think, a really good mental model for how a sampling profiler works, and it explains a lot of the quirks that profilers have, that they might miss some method calls. You might not see a method call if it returns too fast, or it's not called very often. And also that we can't see where methods start and stop. And this isn't, well, I mean, I wrote this as pseudocode, but it turns out this does kind of work. So if you try to run this against a program that's a simple program, for example, if we're doing sleep 1, the pure Ruby sampling profiler is able to run alongside just fine. It will wake up every 1 millisecond, record a sample, and go back to sleep. And at the end of this, sleep 1 will end up with 1,000 samples, right? One sample, or 1,000 samples for 1 second. But if we make it a little harder, and we replace our sleep 1 with a loop that takes the same amount of time, It also takes 1 full second, but it just spends its time looping and being busy. This won't actually work. Our sampling profiler in pure Ruby will end up with GVL contention, and it will not be able to run. Ruby has a global lock, the global VM lock, which only allows one thread to be executing Ruby code at a time. That might sound worse than it is. We can run I/O in parallel, or sometimes C functions can be run in parallel. But Ruby code, we can only have one thread at a time. And this is the problem we're running into here. In Ruby 3.2, Jean Bussier by Root introduced a API for GVL instrumentation, and Vernier also subscribes to this. You can configure it like this. There's a add event hook API, and there's different hooks we can listen to see every time a thread moves to a different state inside Ruby. This, like the GC information and the user timing, is displayed in our marker chart, so we can actually see where a thread was stalled. And we see that it was our sampling profiler was stalled for quite a while, a whole 100 milliseconds, even though we wanted it to wake up every 1 millisecond. And we can find that constant inside Ruby. That's 100 milliseconds is the time Ruby will allow a thread to run before preempting it. So Vernier reports these GVL states in three possible states. A thread is either running, it's holding the GVL to execute Ruby code, it's stalled, like our sample thread was here, it's blocked, it wants to acquire the GVL, it's ready to run, but another thread is running and it has to wait for it to give up the lock. Or it can be suspended. The thread doesn't hold the GVL because it's doing I/O or sleeping, network, things of that nature. One thing we realized we could do in Vernier is we can record a backtrace whenever we reach the suspended event. We know that the Ruby program cannot move forward when it's suspended. It needs to hold the GVL in order to run Ruby. So we know that the backtrace it has when it releases the GVL is the same state that thread's going to be in until it gets the GVL back. So we're able to show that in the marker chart as well. And this actually ended up as one of my favorite features of this profiler, which is that if you're using a properly written C extension, it will release a GVL every time it does I/O. So we just automatically get instrumentation that's very accurate for where I/O is happening in our program. This example is from bundler we were looking at earlier. This is the HTTP request it makes. Okay, so our pure Ruby sampling profiler doesn't work. Let's look at a real profiler. This is StackProf, which is the profiler I've probably spent the most time with, at least before writing Vernier. So StackProf works based on Unix signals. So a Unix signal comes in and it starts running the signal handler code that StackProf has set up. Now, Unix signals are really, really weird, so you can't do much of anything inside the signal handler. You can only run functions which are designated async signal safe, and that means that does not include allocating memory, so you're very limited. But Ruby provides a postpone job API that lets us ask the VM to run some of our code a little bit later, when the VM's reached a state where it's safe to allocate, safe to run extra code. So we queue up one of those jobs, and then at some point later, we hit the safe point by calling Ruby VM check ints, and then we run more of StackProf code that will call RB profile frames to figure out the stack we're on, and then it will do some allocations to save that sample. And this works fairly well. This totally works with Ruby code that holds the GVL, but it has a weird effect. Here's an example program where we're doing a bunch of medium expensive string operations, and then we're calling an empty method, which is totally empty, so should take no time at all. The problem with StackProf's, the way StackProf would handle this is that there's actually only 2 safe points in here. There's one at the return of empty method, and there's one at the return of slow method. And the return from empty method happens before the return from slow method. So even though we were doing all of this expensive string work in slow method, that gets blamed on empty method. It would report that 100% of our time happened there, which is not true. So a couple years back, I fixed this in StackProf with something that could be considered a hack, which is that we moved RB profile frames from that check-in safe point into the signal handler. And the problem with this is that RB profile frames is not officially async signal safe. However, in the Ruby virtual machine, in practice, it has been safe since Ruby 3.0. A change was made so that the stack's updated atomically. I don't know if it was done intentionally, but it's nice that it was. And in YJIT, it's been safe to do since Ruby 3.2. So this isn't a very satisfying answer. I think there's more work and more decisions we need to do here, because there should be a way that's officially supported to sample accurately. But at the moment, I think all profilers are sort of using this API in a not officially supported way, but that is necessary to get the kind of accuracy that we want to have. Another problem with the postpone job API that's a bit weird is that if you have a program like this, where we do a very big while loop and we're testing it with YJIT, the postpone job will actually cause YJIT to side exit. And this is a very extreme case. You'd probably only see this in a super micro benchmark, but it can actually make the program run much slower by affecting the way YJIT runs. And I don't think this would be a massive issue in a real program, but it's just generally, postpone jobs are a way that affects the program runs in a way that we don't want. We want to try to be as hands-off to the program we're measuring as possible. Okay, so we've solved safe point bias, but there's yet another problem that using postpone jobs has. If instead of Ruby code, we have a C function that a single call to it takes a very long time, we won't reach the safe point fast enough. And in fact, if more signals come in, we'll end up missing samples. And those will just get dropped without being reported. Or we'll report one. There's only, StackProf only holds a single profile in its buffer. This is something that I think Vernier finally solves adequately. We've reintroduced another thread, but this time it's a C thread rather than a Ruby thread. So we have no problems with GVL contention. This thread is responsible for sending a signal to the Ruby thread, waiting for it to call RB profile frames, and then saving the sample that buffers up. We're able to do this because using the stack table infrastructure we set up earlier, that never does any Ruby allocations, so it's safe to do in a C thread. And this means that we never miss a sample and we're more accurate. We also have less overhead because the saving of the sample is able to be done off the main thread. We have our own dedicated thread for that. Another problem Vernier is able to solve is threads. For a long time, StackProf and other profilers weren't really thread aware at all. They just profiled the main thread. That might have worked when most web servers were single-threaded, but I think most people are running a threaded web server nowadays. And so that the profiles have any information at all, we added a hack to StackProf a while back to just forward signals onto the thread that started the profile. So that made some profiling work, but it was still very inadequate. If there were more threads running, we wouldn't capture any information about them or know how we could improve them. Initially, that was one of my main goals with Vernier. So from its thread, it was able to send signals to each of the Ruby threads that's running and then collect the samples back from them. And this worked well But one of the problems this had is that, again, we're introducing more overhead. We're sampling threads which we don't need to sample. And I was worried this would discourage people from adding more threads. I could easily see if you added 100 threads, this would become unwieldy and the sampler would no longer, or the profiler would no longer work properly. But we realized there's a trick that allows us to avoid most of the work this did, which is that we're already subscribed to the GVL API. So we know when threads are idle. And we know that when threads are idle, they can't move forward. They can't run more Ruby. And we also recorded the backtrace when it first went idle. So we actually don't need to signal those threads or profile them at all. We know exactly where they're running at all times because we used a combination of tracing and sampling. However, there was use out of that. If we also are running, when we're running Raptors, we do have multiple threads that are running at the same time with the GVL. So that code is still in place, and we're able to use that to measure all Raptors which are running, all threads which are running, with minimal additional overhead. So being able to see all of these threads gives us a new way to profile. Instead of having to rely on profiling a specific request, we can now profile our entire web server for a period of time in production. Here I'm running a Rails server listening for a signal, and then we can toggle profiling on and off by sending that process a signal. Here's my personal Mastodon web server serving multiple requests, and we can see here that it's suffering from GVL contention. Here it's serving its first request and running along fine, but then later it ends up stalled on what looks like it would otherwise have been a very fast request, but that got inflated into a 100 or 200 millisecond response time. Switching over to the other thread in this process, we see that the positions are swapped. Now one thread is running, where one thread was running, the other is stalled. In a non-GVL aware profiler, this would have just appeared as mysterious slower queries or other I/O operations. And now we can tell clearly that this is caused by GVL contention. And that would have been very confusing because there's no improvements we could make to the stalled thread in the time it's stalled to make that run faster. The problem exists in the other thread. Oops. So there's a few options we could use to solve this problem when we now see it occurring. Probably the traditional advice would be to use separate processes. And that probably makes sense if we're regularly seeing this type of things. We want to reduce the threads to our Puma worker, use separate processes instead. The other option we have is we're still a profiler. We could try to make that running section faster. If we look at the thread that is using the GVL in the time we had that contention and try to make it spend less time using the GVL. But I think this gives us an interesting third option. We could use a short-lived Raptor. Last year at RubyKaigi, Koichi mentioned that there was difficulty getting wider adoption of Raptors. And it's true that unlikely anytime soon major frameworks and large applications are going to be able to put their entire request response lifecycle inside of a Raptor. But I'm hoping that GVL-aware profilers might be the missing piece of that puzzle. We can use a profiler to determine specific locations that are keeping the GVL locked for a long period of time. And then we have the choice to either make them faster or to extract them into a Raptor to help improve our concurrency. So in summary, Vernier is a GVL-aware profiler, which is able to profile all Raptors and threads with very little overhead and minimal interference. It supports GC tracing, GVL tracing, user tracing, and allocation tracing. I hope you give it a try. Let's make our Ruby code fast. Arigatou gozaimasu.